Now I have some review of geometrical imperfection accounted in different standards. For example, in AP standard, it's American standard. Out-of-roundness is a very common defect in pipelines. So how we can account for it? In AP there is some formulas, but as I can show, there are not so good one because they account for equal angular segments. And if we apply this procedure to a perfect circle, but we have some shift on the center in measurements, we generally have the shift in our real measurements. So we will have an fictive additional stresses. Another issue is offset misalignment in longitudinal wells. Also in AP we have just an empirical formula which doesn't give us the full pictures of the stress strain of this pipe. And also how we can distinguish from local to global angular misalignments. Here is our framework for measurements of out-of-roundness without, we don't achieve any fictive coefficients and fictive stresses. Also, in our opinion, we have to account for manometric effect. This effect came from bend analysis. When this bend under pressure is wants to be a straight one, it's changes its form. So if we have a shell with geometric defects, it also will have this manometric effect. Also, we have to account for pipe flexibility, and now I will talk about Mitred bend. Here is a sketch from SMS standard, and I will talk about our model for this single Mitred bend in case of that it is a defect when in the field we have to weld two pipes. We always will have these angular distortions between these pipes. So I will start with the description of shell models, and then we'll go through all these points to analysis of Mitred bend. So again, we'll have a sketch for stress resultants, equilibrium forces, geometrical physical equations. But now we won't solve this equation directly. We will divide it into two equations of force order, which it can be easily solved. This will be done by assumptions. We will divide our solution on a short one and long one. Short one is with this assumption that any geometrical force function in circumferential direction change much less than in axial direction. This is the main assumption. And applying this assumption, we can arrange our forces and displacements, and we can neglect some of our components. And in result, we will get an easily solved equation of a force order. Here is the general solution of these equations. We have neglected the rising terms, only decaying terms. So this solution is quite common to equation for asymmetrical end effect. And here is the explicit form of our main variables, which we will need in our further analysis. Long solution, the same one, but another assumption that any geometrical or force function in axial direction change much less than in circumferential one. Again, we will arrange our forces and displacements, and we have the similar equations but different coefficients here. The same form of solution, again, we neglect the increasing terms, only decaying ones. And why this solution is long and that one was short? This long because it's slowly decaying in the axial direction, but the short solution is quickly decaying. Again, our main variables for our analysis, and here is some comparison between our solutions. I have simplified the main equations, and here is comparing by wavelengths, by the main equations, by the forces ranges. And again, short solution is more similar to axisymmetrical end effect, and long solution is similar to Vlasov semi-membrane theory. To come into our Mitred band, we will need some boundary condition. So here is the force projection for this Mitred band. Here is the general form of our boundary conditions, and let's look at the Mitred band under internal pressure. In this case, we have only two loadings, and we'll have only two boundary conditions. These boundary conditions are for n equals 1. In addition, we have this condition. And for Mitred band under internal pressure, we will start from a short solution. We'll get all these constants, and the condition for shear force is satisfied automatically. So our long solution isn't needed here. We just have only short solution. And here's a comparison with the experimental results and the FEM solution. Experimental results are with these dots, and the solid lines are our analytical solution. The dashed lines are the FEM solution. As you can see, they're quite in good agreement. And here is an explicit form of stress concentrations. Mitred band under bending moment. Another case of loading, and this time we have these two boundary conditions. We have this boundary condition for n equals 0 and n equals 2. Again, we will start with a short solution for n equals 0. And I won't stop at all of these equations, just to give you the idea of our solution. So the idea is that our starting with short solution, we came to the long solution. They are connected by these shear forces. And then this long solution can give us an additional short solution for n equals, we started from n equals 0, then n equals 2, then we will go to n equals 3, and we will stop at this level. And again, here are some comparison with numeric results and experimental data made by, these experiments were made by Ferrer and Glaze. Again, we can see a good coincidence of analytical and FEM solutions. And these results are for Mitred band under pressure and moment loading, so it's just a superposition of our equations. And here is some form of FEM solution, and come for more conclusions.